Hello, hello everyone. I'm Nahuel Palumbo. I'm part of the Pharo VM with Guille, who talks before, more people. And I'm here to talk about ordering optimizations in a meta-compilation of primitive methods. Okay, you have my email there. So okay, I'm working in the Pharo VM team. And the Pharo VM is complex in Shine, has a lot of parts, and a lot of complex parts. Guille was talking about how to test the garbage collector that is here. But me now, I'm focusing on the runtime environment that has these two components, that is the interpreter and the sheet compiler. What this means? This means that when you want to execute Pharo code, you can execute it in the interpreter, that is a bytecode interpreter, so interpret the bytecode that performs the operations. And at some moment, maybe the system say that your code is a hotspot code. That means that we can compile it to machine code to run faster. We say, okay, we will compile this code and run it faster in the just-in-time compiler, sheet compiler. And in both cases, we have some primitive implementations, primitive of the languages, normal primitives. What happened here is that these two components make different things in different ways, but at the end, they perform some kind of similar logic. You can think about that if I execute my code, I don't care if I execute it if it is executed in the interpreter or in the machine code or in the sheet compiler, it will perform the same computation. So there are some kind of relation between these two components, but they work completely different. For example, the interpreter will use the stack, an operand stack, and the sheet compiler use the register on the computer in the architecture. So one problem is that this guy, the sheet compiler, is harder to maintain. So it's hard to understand and it's harder to maintain. Maybe we can, I don't know, an idea that we have is maybe we can generate the sheet compiler code from the interpreter code. If I write the interpreter and the sheet compiler should do the same in a different way, where maybe we can transform this way that how the interpreter works to the way that the sheet compiler should work. And this is how we start with this project that is Druid. This part of my PhD that I'm starting in the next month. Okay, and we start to generate the primitive of the language. The idea basically is both the interpreter and the sheet compiler are written in Pharo. So the primitives in both cases are methods, different kind of methods, so that perform it differently. But the general idea is, okay, I can take one primitive from the interpreter, take the AST, so see the code, make an abstract interpretation of this code, and we generate an intermediate representation that is the Druid intermediate representation that is a control flow in a SSA form. So here you can think like this, like a control flow graph with boxes, and inside the boxes there are many instructions. And these instructions are close to machine code instruction, if you want to think about it. When we have this intermediate representation, we run optimizations on it. And at the end, we generate the sheet compiler code from there in the Meta-Compilation. And with this method, is the sheet compiler code, we put boom here, and then we can start to build the sheet compiler from the interpreter. This is the general idea. what I will talk about is about this part when we optimize the intermediate representation, this control flow graph. And well, we have some implemented optimizations. I will not talk about them. You can find them in the bibliography. Is common optimizations in the state of the art of compilers. But some important thing is that these optimizations work together. So they perform itself. What they do is they have an effect on the intermediate representation. So they change this graph. They will change it. And they change performing one optimization each, but mixing them, you can arrive to better or more optimized code in different ways. So what happened is maybe some optimizations open the way or the opportunity to others implementation to optimize the code. And this relationship between the optimizations is not easy to determine. So when we implement all of them, and we have to apply them to a primitive, and we have to decide an order. Okay, what is the order? And okay, we start to play, and we say that this order is not easy to determine or to think about that. It's a complex relationship. It's not easy to determine how they will work together at the end, a priori. No. So for show an example, I have this little example. In this graph, we see I took three optimizations, three different kind of optimizations, if you want, and I made all possible orders, the 6 possible orders to apply them. And we applied it to one primitive. So here in the y-axis, we can see the number of instructions. This is important for us because this is our metric to know if an optimization really optimize the intermediate representation. We say that it is optimized if at the end you have less number of instructions. If you can do the same with less instruction, okay, this is an optimized form of the code. And we can see here how all the seeds go to different ways, like the chaos appear in this sequence. So we can see that the 6 combinations finish in 6 different intermediate representation with 6 different number of instructions at the end. And we also see if you don't choose the correct order, maybe you finish with more instruction than at the beginning. So in these 2 cases, we finish with more instructions than the beginning. So maybe apply these optimizations in the wrong way is worse than not apply at all. So this is a difficult problem that is now in the bibliography as the phase ordering problem. Okay, so our first approach was, okay, so let's make a sequence, as we know. I don't know. We developed most of the optimizations. We know how they work, so maybe we can start to think and to think a lot. And at the beginning, this was very, very nice. It works. But as we start to support more primitives, then we need to implement more optimizations. And okay, we can put this here, and then more primitives and more optimizations. And something that happened is that this list is the same for all the primitives. So we have only 1 second for all the primitives. That this can be from an hypothesis that we have that okay, order optimization for any kind of program is very difficult, but maybe find an optimization sequence for the primitive of the language for our code, that maybe that could be more easy in the sense way that it's possible to find it because they the code is not so different between the primitives or between some kind of primitives. For example, the arithmetics make the sum, okay, take two numbers, checks, make the sum, check overflow, okay, the multiplication make something similar, or the subtraction, okay, so make something similar. So we start with this. Somebody's calling me now. But build the same, have the same sequence for all primitive. It's a different task because, okay, now we have this primitive, this sequence work for this one, but not too much for this one. So, okay, move this here. No, okay, well, repeat this twice and maybe, and then numbers, machine numbers. And in one sense, it is not possible to maintain this manually. So here start to be a problem. So what we start to do is to implement automatic strategies to find this sequence. So the first strategy was a search-based strategy that is a high-climber algorithm. What it does is take an intermediate representation. From one intermediate representation, make a lot of them, applying one by one the optimizations. So if we have, I don't know, 10 optimization, from one we have 10, we finish in 10 new control program, and the algorithm compare them with our metric, that is the number of instructions. And if it says, okay, this has less number of instructions, okay, this is a good optimization to apply, and we repeat it until there are no better or optimized code. So at the end, you have a list, a sequence of all optimization that was chosen by one for the algorithm. This part of choose, okay, which is best, or what is better, or which optimization I choose is complex. It has like 3 levels, in which the first one tries to just reduce the number of instructions. If the optimization don't do that, it will never chosen by the algorithm. So the first level take that. The second level has the propagation. Maybe when I propagate a constant, I don't know, to solve an arithmetic equation in the compile time, you can propagate solving, and you don't reduce the number of instructions, but you left that code that could be reduced after. So here we see how they play together. So the second level includes the for example, the propagation that doesn't change, but after yes, doesn't change, but after yes. And the third one made some code splitting or duplication of code to be reduced in particular scenarios after. So we can see how it's difficult to search in this space because it has a lot of local minima that are easy to find, but there are only few good optimizations, and you have to go around the local minima to find them. So this heuristic try to help the algorithm to find them. And it was nice, but it takes a lot of time. So to search and to search and to search has a lot of time to run it. That for production, we doesn't care so much because we do this ahead of time. So we are compiling the sheet compiler. So we first compile the sheet compiler and then we run the virtual machine. But for example, for testing, yes, this is insane. I cannot wait too much just to run a test. So for the development, this is important. So we build another strategy that is the predictive.
We have 2 minutes. Yes, yeah, sorry.
No. This predictive strategy, what it does is look the form of the intermediate representation and try to guess which optimization could have an impact or an effect of them. or in the reverse mode, okay, if the code that I'm looking for have no constants, so I will not perform the constant propagation. That is the same. So try to filter the list. It select so it's the phone. It selects some optimization and apply all of them to have the new intermediate representation and continue. And it finish when this the result is not better than the original. So have more or equal number of instructions. And at the end, you have these chunks of optimization that when you concatenate, you have the last list. So this is another strategy, and we can see here how it arrived to the same result in a different way. There are another do a different way, but okay. At least we come back to the idea to share the same sequence of optimization with many primitives. So what we did is, okay, we run the first strategy, so to the search-based strategy with all the primitives and generates all the sequences of optimization, and we choose the longest. And we say, what happens if I choose this and I apply this to all the rest of primitives? So we have these three, and we compare with the manual, with the first one, when I start also the problem. And we have these two results, and when I finish in 2 minutes, we have these two results. In this graph, we see each color is each strategy. The first three are different configurations of the search to select the first optimization, last optimization, or the best optimization to optimize in each iteration. The primitive, and this is the fixed list. And something, and all this graph is relative to the manual strategies. So here in one is which is the number of instructions at the end. So after applying all optimizations for the manual strategy. So this is the one. And what we can see is that most of them arrive to the same graph. So all of them, all the strategy, the manual and the automatic, arrive to the same graph for most of primitives, but not for the most complicated or the most complex one. For the most complex one, our manual that was built by the developers, so by experts that know how works all the optimization and how to mix it, and has a lot of work. Okay, make a better effort, but for example, our the best search is the closest to that only have an average of 14% more instruction than the manual. That is okay because okay, don't arrive to the same optimal result in all the cases, but it's automatic. I have not to think about or to maintain all the list. This is in one way, and in another sense is, okay, they arrive to the same optimal result, but how fast, what is the rate of convergence to arrive there? How many optimizations each strategy has to apply to arrive there? And okay, these are the results. These are raw results. Here we have the number of optimizations, the primitives, and each color is the strategy. The blue one is the manual. What we can see here is that there are a pattern. So our idea to reuse the same optimization list is not too crazy because we can see this like group of patterns. Maybe not one for all, but maybe we can search for one primitive and reuse in a certain group of them.
We really need to close. Yeah.
Okay, and in this here we see that the predictive is faster, so it's faster than the manual in an average of 21%. Okay, so we see this. We say that the order of the optimization is important. We say all the strategy, and we saw that have an automatic approach to select the sequence of optimizations is possible is good enough. Maybe in the future we can mix all these strategies that now we compare by itself. And thank you very much. I'm here for questions. Sorry for the late.
Thank you, Nahuel. And it was a very interesting talk. And we have some minutes for questions. And I will do the first one because this is my right. No, not really. But the question is, why is the number of instructions a sensitive measure of performance, or the quantity that you want to optimize for?
Sorry, what's the question? What is the number of instructions?
Why the number of instructions is the quantity you want to optimize for?
Okay. Yes, that is a good question. That is a first one because it is easy to know. This is a number easy to calculate for an intermediate representation, and less instructions means that so when you, because from here you generate the code for the sheet compiler, and the sheet compiler, when it has to compile a method or a code, normal code, it will generate the machine code for your specific target architecture. So we are generating the template to generate the machine code. So if we generate the template with less instructions, maybe we can optimize better this sequence because the code is smaller. So you have more chances to continue optimize to a specific target, for example. If you have more instruction or the logic is in more instruction, it's more difficult to continue optimize it. So that, but we can have another numbers. So now we do it with this because it was the easiest and good enough measure to have from the intermediate representation, but we can have more, for example, the number of paths or the number of connections between the blocks, or point or have a value for each instruction. Maybe there are instructions that are less optimized than another, and that's all. But how we are generating the template and then the sheet compiler we generate for each architecture is not the same. Maybe different architectures are different optimizer in the different ways. So it's complex, but it's a good question. Yes.
Thank you. Is there any other question? Juan?
Yes, hi. Have you tried applying this kind of approach, not to the intermediate representation, but to the cheat compiler itself, or at the machine instruction level?
There are some kind, we did go through there, but there is some kind of optimizations, smaller optimization that apply when you have to transform the sheet compiler template to the specific instruction for the architecture. Sometimes there are no an equivalent between the model of the sheet compiler and the instruction that support the architecture, and you have to I don't know, make some different so split one instruction in many, and you can play with that. We are not optimized at that level, but is an option also. Now we are in the like a more general level. But yes, there are opportunities there to optimize also. Yes.
Any more questions?
I have a question, which is this something, is the idea to replace all manual optimizations, or is the idea to automate the hard work and then let the experts do the final tweaks?
Okay. The point with this is that you don't need to be, the idea is that you don't need to have a knowledge, to know a lot how the sheet compiler works to to maintain the VM or to make a pull request to the VM. Now what happens is if I want to create, for example, a new primitive at the VM level, I have to implement it in the interpreter to understand how the interpreter works and implement it. And then I have to understand and implement how the sheet compilers work and implement it and so on. So that is one of the main points to have this automatic approach to only maintain one of them. And then what happened now is when you read the code of the sheet compiler, for example, that are handwritten, there are a lot of optimizations there. There are a lot of this optimization there, but we're manually thinking and wrote the code in the optimized code. But when you read it, you have to read it a lot and spend a lot of time to understand, okay, she's doing it is doing this in this way because it is optimized for that way. So maybe the code from the interpreter and the sheet compiler for the same primitive are very different, and you start to think why it's not like this or like that, and why here is doing this. So there are a lot of questions that appear when you read the sheet compiler code because it's optimized by hand. Maybe if we can organize the optimization and say, okay, see how it is mutated when they apply is to better understand what is happening at the end.
Okay,
So yes, focus is are in the developers, I think.
Thank you.